Hello everyone, I am Naranshana and today I am presenting a very important concept in database system, RAID in dbms, which stands for Redundant Array of Independent Disk. This technology plays a key role in ensuring both performance and reliability of our storage system. Next, we see the introductions of RAID. RAID is a storage visualization technique that combines multiple physical disk drivers into a one logical unit. It's crucial in environments where data availability, fault tolerance, and performance matter, such as large-scale database. With RAID, even if one disk fails, the data can still be recovered without any interruptions. And next, we discuss about the introductions of data storage. As data volumes grow rapidly in modern applications, and managing how data is stored becomes more crucial or critical. A single point of failure can lead to massive data loss. That's why technology like RAID are essential. They provide a buffer against hardware failures and improve the database performance by efficiently managing the read and write operations. Data loss can be catastrophic in mission critical systems. Database performance depends on speed and availability. And next, what is RAID? RAID turns multiple disks into single logical unit and it enhances the fault tolerance. It uses three core techniques: stripping, which spreads data across the disk for speed; mirroring, which duplicates data for safety; and parity, which helps recover the data in case of failure. Data is distributed using a technique like scripting, mirroring, and parity. And next we see the history of and evolutions of RAID. The RAID concept was introduced in 1987 by researchers at UC Berkeley. Initially it was called Redundant Array of Inexpensive Disk as it focused on using low cost hardware. Over time, as disk cost fell and reliability became more important, it involved in independent disk. Evolved to independent disk or cost is no longer than the primary factor. And next we see how RAID works. To understand RAID, think of it like a group of teammates. Instead of one person doing all the works, multiple disks collaborate. Stripping speeds things up, mirroring products against the failure, and parity acts like a backup brain that can cull or rebuild lost data. The combination of these gives us both speed and safety. Here, the RAID uses different technologies like stripping, mirroring, and parity. In first stripping, it's spreading the data across the multiple disks. It is the works of stripping. And next mirroring, it copying the data to two or more disks. And next parity, it checks the error and data recovery. And next, categories of RAID. There are two categories of RAID: hardware RAID and software RAID. In hardware RAID, managed by dedicated controller card and better performance, and software RAID managed by the operating system, cost effective for smaller systems. In hardware RAID, which uses a physical controller card, offering a better performance but at a higher cost. Then there is software RAID, which is handled by the operating system. It's more budget friendly and ideal for smaller setups. Types of RAID levels. There are up to 6 levels: RAID 0, RAID 1, RAID 2, RAID 3, RAID 4, RAID 5, RAID 6, and RAID 10. First we discuss RAID 0. This is called stripping. It splits the data across the disk for speed, but it has no redundancy, so if one disk fails, all data is lost. It's fast, but it risky. Minimum 2 disks is required in the RAID 0 stripping. Let's see the diagram of RAID 0. This diagram shows how RAID 0 works through the stripping. Here the data is divided into blocks. A1 goes to disk 1, A2 to disk 2, A3 to disk 1 again, and so on. There is no duplications or parity, so it offers high speed. But remember, there is no fault tolerance. If any one disk fails, all data is lost. And next, RAID 1. It is also called mirroring. Duplicate data on two disks. High fault tolerance, slow write performance, and minimum 2 disks is required. It is very safe, but because every write is done twice, it is lower than write 0. In write 1, how the diagram works. It is also called mirroring. As shown in the diagram, every piece of data is copied to the both disk. So A1 is on both disk, A2 is on both, and so if one disk fails, the other has a full copy. It gives great reliability but uses double the storage. And next, write 2. Now comes write 2, which uses the bit level stripping and hamming code for error corrections. It extremely precise, but because it requires all the disks to spin in sync, it is rarely used today. Still, it's important historical for introducing advanced error corrections. RAID 2 uses bit level stripping, meaning data is split at the bit level. As seen here, multiple disk storage, individual bits data, and some disks are used for hamming code based error corrections. It is quite complex and requires synchronized spinning disks, so it is not commonly used today. And next, write 3. Write 3 uses the byte level stripping and stores all the parity on a dedicated disk. It is ideal for big and continuous data like video streaming. However, it's less efficient for small files, and the dedicated parity disk became bottleneck. And next, write 4. In write 4, it improves on write 3 by using block level stripping. This means it reads and writes larger chunks of data, but like write 3, it still uses the single parity disk, which can slow things down under heavy loads. And see the diagram of write 4. Write 4 uses the block level stripping, which means each disk stores whole blocks like A1, A2, A3, and one disk is dedicated entirely for parity. It allows independent reads, but again all writes must go through the parity disk, creating a performance bottleneck. And next, write 5. Write 5 fixes the bottleneck by distributing the parity across all disks. It balances speed, efficiency, and fault tolerance. The most commonly used write today. Write 5 is most commonly used write today. It has minimum 3 disks required. See the diagram of write 5. In write 5, the parity information is distributed among all the disks. As you see, each disk not only stores all data blocks but also parity for other blocks. This avoids overloading a single parity disk and improves the performance while still maintaining the fault tolerance. And next, write 6. Write 6 takes write 5 one step further with two parity blocks. It can survive two disk failures system where uptime is critical. We see that how the write 6 works in the diagram. Write 6 is similar to write 5 but has two sets of parity, which allows it to tolerate two disk failures. The diagram shows the parity being distributed twice across the disk, making it one of the safest options, especially in critical enterprise or enterprise environment. And next, write 10. Write 10 combines stripping and mirroring. It's both fast and safe, but need at least 4 disks. Think of it as the premium write setup for serious performance and reliability. We discussed the diagram of write 10. Write 10 is a hybrid of write 1 and write 0. As the diagram shows, the data is first mirrored write 1 and then stripped write 0. This means it gives both speed and reliability. However, it requires a minimum of 4 disks, so it's best for performance critical setups. And next, to discuss the advantage of write. Write brings several benefits. It improves read rate, speed, system availability, even during the disk failure, and scalability. It is a cost-effective solution for business that rely on uninterrupted access to data. It continues the access to data during disk failures. And next, limitations of write. However, write is not perfect. It requires careful configurations. It adds cost due to extra disk and hardware. And remember, write is not a backup. You still need regular backup for disaster recovery. Hardware write can be expensive. Write is everywhere, from cloud providers like AWS and Azure to banking system, hospital database, and even streaming platform like Netflix. Any system that handles sensitive or large amounts of data relies on RAID. And next, future of RAID. The future looks promising with RAID integrity with SSD, AI-based failure protections, and hybrid system combining software and hardware for smarter storage. And next, conclusions of RAID. To sum it up, RAID means speed, safety, and stability. It is a critical technology in today's data-driven world, whether you're storing videos, transactions, or government data. RAID ensures your data stays inaccessible. Ensure the data integrity, performance, and uptime. Thank you.